Welcome to this video on the topic of binary numbers. In this video I'm going to show you two new concepts. The first one being how we can represent negative decimal numbers in the binary number system. And then secondly, how we can perform subtraction using binary numbers. Now, first example here we have the number 83 and its decimal or its binary interpretation over here. Now the question at hand is, how can we represent negative 83 as a binary number? Now the way in which we're going to do it in this video is we're going to use a representation system called 2's complement. Now 2's complement, it's typically the system that most computer systems use to represent negative numbers. However, it's not the only system you can use to represent negative numbers, but we're going to use it because it's actually the system that our phones use. It's a system that most of our modern Windows computers use, and it's actually a pretty straightforward way to do it. Plus it makes arithmetic very easy going forward. So first step in 2's complement is we're going to flip all of the bits in our positive number. What do I mean by flip? Well, if we see a 1, we're going to change it to a 0, and if we see a 0, we're going to change it to a 1. Now, at this step here, what we actually generate is something called 1's complement. But we don't want 1's complement, we want 2's complement. So we move to the next step, which is after we flip all the bits, we add 1. And thus we get 2's complement, which is the representation of a negative decimal number in the binary number system. So, to start off, we get the positive interpretation, flip all the bits, and then add 1. Alright. Sounds reasonable enough. We'll start with 83 base 10, and its interpretation is 0, 1, 0, 1, 0, 0, 1, 1. Now what we're going to do is flip all its bits about. So we're going to change the 1 to a 0, and the 0s to 1s. Seems reasonable, and we said that this was 1's complement, like so. Alright, so if that's 1's complement, that's awesome, but we want 2's complement because we want a negative number. So what I'm going to do is write out my 1's complement, then I'm going to add 1. So, doing the result, 1 and 1 is 1, 0, so I'll put a 0. And carry the 1. This will be 0 and 1, which is 1. And now we don't have any more arithmetic, so we just let our digits fall all the way through, like so. And thus, what we find is our negative interpretation for 83 is 10, 10, 1110. So negative 83 base 10 is equal to 10, 10, 1110. Now, next thing, if you try to verify this using the programs that we've used in the subsequent lessons, what you're going to find is that this is going to come out as a positive number and not negative 83. Reason for this is that when you're working with negative numbers on a computer, you actually have to tell the computer in advance that it's working with a negative number. Now, the name for these sort of numbers is, we call them signed integers. And they're used to represent both negative and positive numbers. Conversely, if you only want to work with positive numbers, then you can get something called a unsigned. And these represent positive only. They only represent positive numbers. If you're working in a language like Python, then you can get integers that do positive and negative, but for the programs above, they've only been designed such they work with positive only integers. So if you try and verify this, it will come out differently. We'll talk about these concepts in more detail in probably lessons in a few weeks' time, so it's a little bit complicated and a bit outside the scope of this lesson. Now going up to example 2 here, we have 22 in decimal, and its representation in binary is 000101110. Now if we wanted to represent this number as a negative, so if we wanted negative 22 base 10, we use 2's complement once again to solve this. So we're going to go 0 0 0 1 0 1 1 0, and to start off we're going to flip all of the bits. So that will become 1 0 0 1 0 1 1 1, like so. So this is 1's. Next step is we don't want 1's complement, we want 2's complement. So we're going to add 1. Set up the arithmetic. Give ourselves a little bit more space to work with. Perfect. Okay. Sorting this out, 1 plus 1 is 1 0, so there's a carry. Then 1 plus 0 is 1. And then all the digits trickle down, like so. Therefore, negative 22 base 10 is rewritten as 1 1 1 0 1 0 1 0, like so. So that's negative 22 in binary using the 2's complement method seen over here. Now, final question, example 3. We want to be able to do 83 take 22, but we want to do it in binary. Now, we haven't done take yet, and it's probably a little bit different to how you'd think it's done in binary. Now, one way of doing it is, let's reimagine this question here, and rather than saying 83 base 10, take 22, let's go plus minus 22, like so. So what we're going to do is we're going to add a negative number to a positive number. So given 83 we know is equal to 01010011, and negative 22 in binary is 111011010. Let's perform the arithmetic. So we'll go 0 1 0 1 0 0 1 1. Then negative 22 is 1 1 1 0 1 0 1 0. We're going to add this negative to the positive. Therefore, let's do the arithmetic. So 1 and 0 is 1. 1 and 1 is 1 0. So put the 0, carry the 1. That will be 1. 0 1 is 1. 0 1 0 1 1 0. So this will be put a 0, carry the 1, and then we're going to get 1 and 1. That's 1 0. So we go 1 bit over. We're now in a 9-bit number. So this is our result. Okay. Now, because we were working with two 8-bit wide numbers and we've resulted in a 9-bit wide number, what we're actually going to do is we're going to omit the 9th bit and we're going to keep the two or these 8-bit numbers here. And this will be our result. So we're going to go negative 83 base 10 take 22 base 10. The representation of that is we're going to go 0 0 1 1 1 1 0 1 1. So what's ended up happening is we scrap this one over here. So scrap overflow. Like so. So our result is 0 0 1 1 1 1 0 1. Alright, now to verify this in the Python program, bring this in, I will go to run, and I'll put in the binary to decimal, and then we'll go 0 0 1 1 1 1 0 1, and lo and behold that's equal to 61. And if I'm correct, 83 take 22 is indeed 61. So what you've seen here in this example is how we can do subtraction with binary numbers and the method in which it's done.